Up until now, we've been putting a lot of effort into developing the axioms of the real numbers. Before we move on to actually constructing the real numbers, I do want to take a step back and start talking about some of the concepts that are at the heart of what real analysis is. In particular, we're going to talk about real valued functions. So in this video, we're going to define what real valued functions are. We're going to show some examples of real valued functions, many or most or maybe all of them that you've seen before. We'll define what increasing and decreasing functions are. And we'll show some examples of increasing and decreasing functions. So the question you may have asked yourself just coming into this course is, what is real analysis? And probably the simplest answer I can give you, it is the study of real valued functions. And what I mean by real valued function is a function f where the domain is an interval in the real numbers and the outputs are real numbers. So your codomain is the real numbers. So here are some important real valued functions. Again, these are probably functions that you have run into at various points in your mathematical lives. Polynomials are some of the most fundamental functions that we've been looking at. And those are polynomials or functions of the following form: a0 plus a1 times x plus a2 times x squared, etc., all the way up to some an times x to the n, where all the ai's are constants. So an example of that is f of x equals 3x squared plus 5x plus 1. So the defining properties of polynomials is these functions, if they're interpreted as actions, they use only addition, subtraction, and multiplication. Rational functions are very similar to polynomials, except they include the ability to divide. So you take two polynomials and divide them. So p of x over q of x, where p and q are polynomials. Here's an example of one such rational function. And so, yeah, these functions use addition, subtraction, multiplication, and division. Algebraic functions is an even broader category. This includes any functions that use some combination of addition, subtraction, multiplication, division, and roots. So you could get some function like this. We have a cube root in there and a square root in there, and otherwise it looks very much like a polynomial or maybe a rational function. And then finally, transcendental functions. These are just functions that are not algebraic. We run into a ton of those in calculus, for instance. These include exponential functions, logarithmic functions, trigonometric functions, and inverse trigonometric functions, among others. So again, calculus is based on real valued functions, and so that's why calculus is so tied to a real analysis. So here are some important calculus concepts that you might remember from the old days that we're going to give a new spin now that we're real analysis people. We remember looking a lot at the sign of the derivative to tell us what the graph looks like and where we can find maximum and minimum points. When the derivative was positive, that told us when the graph was going uphill, the function was called increasing, and when the derivative is negative, the function is called decreasing. We had optimization problems where we tried to find the maximum or minimum values of the function. Those are things that we are going to just touch on towards the end of the semester, but we'll define some of the important concepts related to those here. So for instance, if you have a function from an interval I to the real numbers, as a real valued function, and if j, a subset of I is an interval, it doesn't have to be the same interval, it could be just an interval inside of our domain. We say that f is increasing on j if whenever x and y are in j and x is less than y, then f of x is less than or equal to f of y. So from a graphical perspective, this tells us that either the graph is going uphill or it's flat. Now we say f is strictly increasing if these exact same things apply, except instead of saying that it's possible for f of x to be less than or equal to f of y, we say f of x is less than f of y. So from a graphical standpoint, this says that the graph is going strictly uphill. We say that f is decreasing on j if, well, very similar, except going in the other direction. If x and y is in j with x less than y, then f of x is greater than or equal to f of y. And strictly decreasing is the same conditions except that you have f of x greater than f of y. So decreasing from a graphical perspective means either the graph is going downhill or flat. And if it's strictly decreasing, then it's strictly going downhill. And then we finally sort of combine these into one concept by saying that f is monotone on J if it is either increasing or decreasing. And we say strictly monotone if it is strictly increasing or strictly decreasing. So if we're looking, say, at the function f of x equals negative 3x plus 2, back in our calculus days, we could say this is a decreasing function because the slope is negative 3, our derivative is negative 3. Anytime we have a negative derivative, we have a decreasing function. But let's see what happens when we try to put this through the definition of increasing or decreasing. So we're going to assume that x1 is less than x2, and let's say we're not sure whether it's increasing or decreasing. We want to see if f of x1 is less than f of x2 or vice versa. So in order to do that, we use one of our inequality tricks. We look at f of x1 minus f of x2, see if it's positive or negative. If it's positive, that means f of x1 is greater than f of x2, and if it's negative, it's the other way around. So we can go ahead and plug in f of x1 and f of x2 into our function. We get negative 3x1 plus 2 minus negative 3x2 plus 2. If we do a little bit of simplification, we end up with negative 3x1 plus 3x2. We can factor a negative 3 out of there. We get negative 3 times x1 minus x2. Now we know that x1 is less than x2, and so if we subtract x2 from both sides, we get x1 minus x2 is less than 0. So if we look then at what f of x1 minus f of x2 is, it is negative 3, which is a negative number, times x1 minus x2, another negative number. A negative number times a negative number is a positive number, so that's greater than 0. That tells us that f of x1 minus f of x2 is greater than 0, and if we add f of x2 to both sides of that inequality, we get f of x1 is greater than f of x2. So what we have just shown is that if x1 is less than x2, then f of x1 is greater than f of x2. That tells us that f is a decreasing function. If we want to be really technical about it, f is a strictly decreasing function. All right, so now I think you're ready to work on the activities for increasing and decreasing functions. Just go ahead and click on the link below this video.